Ladies and gentlemen, let me introduce myself. My name is Sebastian Dudek, and I am lecturer and PhD student at Curie-Sklodowska University in Lublin, in Poland. And since 2018, I've been working on my doctoral thesis at the Department of Inorganic Chemistry under the supervision of Professor Dorota Kołodyńska. Today, I would like to talk about the poster entitled Enhanced Arsenic Removal by Commercially Available Ion Exchanger Modified with lanthanum-free Ions. Arsenic contamination of groundwater is a serious global problem, as the biggest one occurs in the southern and Southeast Asia. And natural phenomena and anthropogenic factors like mining, fossil fuel combustion, employing pesticides are responsible for that. Long-term exposure to this element can lead to various detrimental health effects. Therefore, the World Health Organization has set the recommended limit of arsenic concentration in drinking water at 10 microgram per liter. In order to meet the WHO requirements, several methods have been elaborated for arsenic removal from water. And it is commonly believed that adsorption process seems to be the most encouraging and prospective method among these technologies due to its convenient operation, low cost, and high efficiency. And once you know that adsorption is the best option for arsenic removal, it was necessary to consider which adsorbent to choose. Unfortunately, commercially available material is not innovative. And in fact, a lot of adsorbents have already been synthesized. So we thought that there was a third option to take commercially available adsorbent and modify it with lanthanum-free ions. This commercially available material was arsen, XNP. It has a structure of polystyrene cross-linked with divinyl benzene infused with nano-sized particles of iron oxide, and it looks like brown spherical beads and has sulfonic functional groups. In the case of modification of XNP with lanthanum-free ions, the same analysis revealed that the surface of XNP after modification became more heterogeneous, and flake-like nanoparticles of lanthanum hydroxide occurred. And the average diameter of nanoflakes was approximately 800 nanometers. So such a morphology could facilitate adsorption onto XNPLA for arsenate-5 ions. In the case of optimization of the modification process, here you can see some important parameters related to the modification process, which was based on the lanthanum-free ions adsorption. And these parameters were as follows. pH was 4. Initial concentrations of lanthanum was 100 ppm. Adsorption time 6 hours. Modification temperature was 295 Kelvin, and also drying temperature 313 Kelvin. We dried our sorbent, modified sorbent for 24 hours. And also we characterized our material. The point of zero charge was equal to 8.29 for the unmodified sorbent, and after the lanthanum modification this value dropped to 7.21. It means that at the pH below 7.21 the surface gains positive charge and it facilitates arsenate adsorption because it forms mainly dihydrogen arsenate anions. And FTIR analysis revealed that after the modification and arsenate adsorption, the new band at about 830 appeared, which indicated evidently the presence of lanthanum-free on the surface of XNPLA. It also suggested that the new bond, arsenic, oxygen, lanthanum, was formed. And also the obtained nitrogen adsorption-desorption isotherms were classified as type 4 according to the UPA classification. So those suggested that both materials, the modified and unmodified one, were characterized by a mesoporous structure. And the isotherms revealed also H3 type of hysteresis loop for both ion exchangers. So this means that these materials have slit-shaped pores. Also, I would like to say something about that is not shown in the poster. XNP LA reached the largest arsenate removal at pH 6. So under such conditions, arsenate ions could be electrostatically attracted because pH 6 is under the value of 0.0 charge. In the case of kinetic studies, kinetic studies revealed that at any given initial arsenate concentrations, 25, 50, and 100 ppm, the efficiency was higher in the case of modified ion exchangers. So this study also revealed that equilibrium was attained relatively quickly, that is about 2 hours at all tested initial arsenate concentrations. And regards to kinetic models, the results suggest that the kinetic mechanism can be described by the pseudo second order model, which assumes that the sorption process is chemisorption. And in the case of equilibrium studies, regards to isotherms, nonlinear plots of Langmuir and Freundlich are presented in the poster. And interestingly, the maximum sorption capacity of the modified XNP was 3-fold greater after the modification. What is more, measured RL and N values indicated the favorable adsorption of arsenate ions onto XNP LA, and the error analysis revealed that Langmuir model described experimental data better than the Freundlich isotherm. And we also tested our material in terms of reusability, and 3 consecutive arsenate sorption-desorption cycles were performed to assess the reusability of XNP-LA. The desorbing agent was 1 molar sodium hydroxide, and after 3 cycles, desorption efficiency dropped non-significantly. So it still had a higher sorption capacity with comparison to the unmodified XNP before the first use. And here you can read some conclusions, but the most important conclusion is that modified with lanthanum-free ions XNP has much better sorption properties against arsenic ions, which leads to its potential application for not expensive treatment of arsenic contaminated water. And that's all. Thank you very much for your attention.
Thank you so much for your question.